In this lecture, we look at the phenomena of spectral leakage and a related concept of windowing. In any experiment, measurements are taken over a finite duration of time. Consider, for example, an experiment in which an instrument records a sinusoidal signal of the form A cosine omega naught t for the time duration t going from minus capital T to t and 0 otherwise. That is, the signal that has been recorded is a pulse modulated cosine function that we have seen earlier, and the time duration is from minus t to t. That is, the underlying signal in the experiment was A cosine omega naught t, which would have continued for an infinite duration. However, we took the measurement over a time interval minus t to t. So the signal for the infinite duration was something like this. However, we recorded the signal only over this particular duration, that is t going between minus t to capital T. So this is the signal, let's say, that was recorded during the experiment. We know that if we were to perform the measurements for infinitely long time duration and we were to do spectral analysis and take the Fourier transform of that signal, that is A cosine omega naught t, then the Fourier transform of that signal, that is given by f of omega, would have two Dirac delta functions at frequencies of omega naught and minus omega naught. That is, the spectrum of the infinite duration signal will have discrete frequencies of plus minus omega naught. However, we have seen earlier that the Fourier transform of the pulse modulated cosine function is actually given by this. That is, the Fourier transform of a pulse modulated cosine function consists of two sinc functions centered at frequencies of omega naught and minus omega naught. So the Fourier transform consists of these two sinc functions. That is, in reality, the true signal, that is for the infinite duration, has two Dirac delta functions at these frequencies minus omega naught and omega naught. And if we take the measurement over a finite time duration of minus capital T to capital T, then these Dirac delta functions are replaced by the sinc functions, and these sinc functions have a characteristic width of 2 pi by t, that is the width of the main lobe of the sinc function. In other words, the sinc functions have a width that is inversely proportional to the time duration over which the signal has been taken. Note that in contrast to the spectrum of the underlying infinite duration signal, which in our case is this A cosine omega naught t, the Fourier transform of the signal that is acquired for a finite duration is continuous, as it has these two sinc functions. On the other hand, we've seen that the Fourier transform of the infinite duration signal in this particular case has just discrete frequencies of plus minus omega naught. In other words, the true signal has this energy that is confined to these discrete frequencies. However, if we take the signal for a finite duration, then this energy leaks over or spills over to the neighboring frequencies. And this phenomena is called spectral leakage. So spectral leakage, in other words, is that you expect that frequency of the true signal to be of, let's say, a particular value, but when you take a measurement for a finite duration of time, then you see frequencies in neighborhood of the true frequency. So there's some portion of the signal that is leaking over to the neighboring frequencies. And one thing to note that is spectral leakage occurs even for continuous signals. So later on we'll discuss that in any practical experiment we'll not have a continuous signal, we have signal that is a discrete signal that has been sampled at a particular time intervals. But this phenomena of spectral leakage has nothing to do with that discrete sampling of the signal. In fact, you've seen over here in this example that even for a continuous signal, you will have this spectral leakage, and the reason is that we have not taken the signal for an infinite duration, and we've taken the signal only for a finite duration. So one should not confuse this phenomena of spectral leakage as an artifact of acquisition of discrete data during the experiments. To better understand spectral leakage, it is useful to interpret the finite duration signal as time domain multiplication of the infinite duration signal, which in this particular example is this cosine wave with a top hat function or a rectangular window which has an amplitude of 1 in the time interval minus t to capital T, and otherwise that function takes on a value of 0. So consider that our original signal was g of t, and we multiply this signal g of t with a function w of t, which we'll call the windowing function. Then if we multiply these two, then we'll get the signal that we acquired over this time interval minus capital T to capital T, and we'll call this function f of t. So acquisition of a finite duration signal during an experiment can be thought of as multiplication of the true underlying signal with a window function which takes on a value of 1 between the time interval for which experimental measurement was done. So why do we need this interpretation that f of t is g of t times the window function w of t? So the answer is that if we look at the Fourier transform of the finite duration signal, that is f of t, or we can also call it as capital F of omega, then it is given by the Fourier transform of product of the underlying signal g of t, which is for infinite duration, times the window function, which in our case is this rectangle window. In previous lectures, we have seen that if we take convolution of two functions and take the Fourier transform, then the Fourier transform is given by the product of the Fourier transforms of those two functions. In this case, we have product of two functions in time domain. Then the Fourier transform is given by the frequency convolution theorem. So the Fourier transform of the product of two functions is the convolution of the Fourier transform of g of t with the Fourier transform of the windowing function w of t, and there's a factor of 1 over 2 pi, and this follows from the frequency convolution theorem. So the effect of acquiring the signal for a finite duration of time is to convolve the Fourier transform of the underlying infinite duration signal, which in our case is g of t, with the Fourier transform of the windowing function, that is, in this case or in any experiment, would be a rectangle window, unless you multiply with some different window, which we'll discuss later on. We have also seen in one of our previous lectures is that the Fourier transform of this rectangular window or the top hat function is 2t times sinc of omega t. So note that in practice you would take time starting from 0, but I'm taking from minus t to capital T because we've done previous examples where we took the pulse modulated cosine function between minus t to t, and if we have a symmetric function and real valued function, then it is easier to plot the Fourier transform because we know that the Fourier transform of a real valued even function is real valued. So that's why we've chosen this time interval minus t to capital T. Otherwise, you could have taken other time interval as well. So we know that the Fourier transform of this windowing function is this sinc function, and we also know that the Fourier transform of the cosine function is given by, in this case, a cosine omega naught t is our underlying function. So the Fourier transform of that is given by a times pi times the Dirac delta function centered at frequency of omega naught plus the Dirac delta function centered at frequency of minus omega naught. And now we are going to convolve this function with the Fourier transform of the window, that is 2t times sinc of omega t. And this convolution operation is trivial, so we get a times t, and of course there's a factor of 1 over 2 pi because this is the frequency convolution theorem. So we have a times t times 2 sinc functions centered at frequencies of minus omega naught and omega naught. And this is exactly the Fourier transform of the pulse modulated cosine function that we have computed in one of our previous lectures. So the point to note is that our true signal had a Fourier transform that consisted of two Dirac delta functions, and then as a consequence of windowing or acquiring the data over a finite time duration, we need to convolve this Fourier transform with the Fourier transform of the windowing function, which is the sinc function. And when we do so, that is, we convolve these two functions, we end up replacing this Dirac delta functions at frequencies of minus omega naught and omega naught with these sinc functions. And that leads to spectral leakage, because now we would interpret, if we have a finite time duration signal, that it consists of this broad range of frequencies, although the true signal would have only discrete frequencies of plus minus omega naught. So spectral leakage is a consequence of windowing. So if we consider a general function or a general signal, let's say g of t, let's say something like this, and we measure this signal only over finite duration of time, that means we multiply this signal, that is the underlying signal, with this windowing function, then it means that what we have measured is only this part in the yellow color, which is my function f of t. A consequence of this windowing operation, which occurs invariably in any experiment, is that if for the true signal, which is shown in this red color over here, if we just look at the single-sided spectrum, let's say the spectrum had some sharp peaks, if we were able to measure that signal over infinite time duration, then the effect of windowing is that the Fourier transform that we are going to get, or the spectrum or the power spectrum that we are going to get, is smoother for the case when we take the signal over finite duration. And in all practical experiments, we would be taking measurements only for a finite duration. And the amount of smoothing that occurs certainly depends upon the duration of the experiment, because note that we are convolving the true signal with this sinc function, which is the Fourier transform of the windowing function, and we know that the width of this main lobe of the sinc function in frequency domain is 2 pi over t. So as we take t to be larger, that is, we take a longer time duration. In other words, if we have a wider window in time domain, then from the uncertainty principle, we know that we will have much narrow sinc function. And if we have a narrow sinc function and we convolve it with the true signal, then we are going to get lesser spectral leakage. That means if I take a large value of t, then the Fourier transform of this broader window is going to be narrower. And when I convolve this narrow sinc function with my Fourier transform of the true signal, then we would see lesser spectral leakage, and that would be the case for any arbitrary signal also. So if we take the signal for a larger duration, then we would expect that the smoothing effect due to windowing is much less, and we are closer to the spectrum of the underlying signal, which we would never measure in any experiment, because we will be doing experiment only for a finite duration of time. That means if in a particular experiment we have to resolve two frequencies which are very nearby, then we need to choose our time duration of the experiment appropriately, so that the spectral leakage is not so much that these two peaks appear to be overlapped in the spectrum of the signal. That means if we want to find whether the underlying signal has two frequencies which are very close to each other, then we need to do the experiment for much longer time. So that's why understanding spectral leakage is important. So in any experiment, you would anyway need to have an idea as to what frequencies you are expecting, and based on that expectation, you'll have to choose the time duration over which you need to do the experiment, and then you can do spectral analysis to find whether you have resolved those peaks or not. So the point is that if the signal has, let's say, two frequencies, let's say omega 1 and omega 2, and we need to resolve these two frequencies, then because the Fourier transform of that signal is going to be convolved with this sinc function with a width 2 pi over t, so we want that Fourier transform of the finite duration signal has distinct peaks. So that means the width of the sinc function, which we are going to convolve with these Dirac delta functions, should be smaller than the difference between these two frequencies. So we must ensure that omega 2 minus omega 1 is much larger than 2 pi over t. That means we should ensure that our time duration, in this case actually 2 times capital T, should be large enough that we are able to resolve these two frequencies. So we would in fact choose our time duration to be such that the sinc function is much narrow than the difference between these two frequencies that we need to resolve. How this time duration affects spectral leakage can be seen from the example of the pulse modulated cosine function. So imagine that we have this pulse modulated cosine function given by this, and I've taken omega naught to be 5 and this time duration minus t to t, where t is equal to 5. So if we take the Fourier transform of this finite duration signal, then we would get these two sinc functions. So if we increase the value of capital T, that is, we take the signal over a larger duration, then we see that we get these relatively sharper peaks at frequencies of minus omega naught and omega naught. That means we have lesser spectral leakage because less of this energy is leaking over to the neighboring frequencies. If we keep on increasing the time duration, then spectral analysis will tell us with more certainty as to what peaks are present in the signal, because we have much lesser spectral leakage in this particular case. So this is how choosing time duration of the experiment can help us resolve frequencies in a better fashion. So we have seen that if we increase the time duration of our experiment, then we can mitigate the effects of spectral leakage because we'll get sharper peaks in our spectrum. Another way to mitigate spectral leakage due to windowing is to choose a window function that has a narrow spectrum compared with the spectrum of a rectangle window. So the point is that in any practical experiment, as soon as you take the measurement for a finite duration of time, you have already done windowing of the signal with this rectangular window. But if we take that signal and we multiply, let's say, with a different windowing function, which is shown over here in the yellow color, with an aim that this windowing function has much, let's say, narrow Fourier transform, let's say something like this. And when we convolve this Fourier transform of the windowing function with that of the true signal, then we would get better spectrum and lesser spectral leakage. So we can choose these windowing functions so that we have lesser spectral leakage. So one such function is called the Hanning window. So the Hanning window is defined by this function w of t, that is given by 1/2 of 1 plus cosine pi t over capital T if we take the measurement between minus capital T to capital T and 0 otherwise. That means this function, the windowing function, which is defined over minus t to t and otherwise it is 0, looks something like this. That means in contrast to the rectangular window that we had earlier, which had an abrupt change at the two ends, this window has a gradual change, and we'll see that if we multiply the signal with this window, it will give us lower spectral leakage. And that's because now we have made the signal smoother at the two ends. So many times the signal is defined over time 0 to capital T. In that case, the shape of the windowing function will remain the same, but let's say if the signal is acquired over t going from 0 to capital T, then the windowing function, which is the Hanning window, would be given by this, where t goes between 0 to capital T, and otherwise the window would be 0. And similarly, there's another function which is very similar, and that's called the Hamming window. So the only difference between a Hanning window and a Hamming window is that, so here we have these factors of 0.5 and minus 0.5 over here. So in the Hamming window, you will just replace this with 0.54 minus 0.46 cosine 2 pi t over t, and we'll see that having these different coefficients will make some difference to the final signal. So how we do windowing is that we acquire the finite duration signal in an experiment, which by default comes with the rectangular window, but because rectangular window is equal to 1 in that time duration, we multiply that signal with this window function, which can be, let's say, Hanning window, Hamming window, and there are many other windows, and that is equivalent to multiplying this Hamming window or Hanning window with the infinite duration signal. And we'll shortly see that the Fourier transform of the Hanning window has much smaller tail, so that when you convolve it with, let's say, a Dirac delta function, then you will get a much narrow peak compared with that you get with the rectangular function. So now what we can do is, to understand the effect of this, let's say, Hanning window, we'll try to compute the Fourier transform of the Hanning window. So the Fourier transform of the Hanning window, which, and we'll continue our example where we take time duration between minus capital T to capital T, can be computed in a straightforward fashion. So the Fourier transform, let's say W of omega, or let's say F of W of t, is given by half of the Fourier transform of not one but a rectangular pulse, because we have this function takes on a value of 1 between minus t to t. So we can just write, let's say, informally, Fourier transform of the top hat function plus half of the Fourier transform of the pulse modulated cosine. And we already know that the Fourier transform of the top hat function defined between minus capital T to capital T is given by 2t times sinc of omega t, and we have a factor of half over here, and then we have half of the Fourier transform of the pulse modulated cosine, and that is given by e times, so we have two sinc functions centered at frequency of pi by t and minus pi by t. So this is the Fourier transform of the Hanning window. Now let us compare the Fourier transform of the Hanning window with the Fourier transform of the rectangular window, which is just a sinc function centered at zero frequency. So let us first look at the Fourier transform of the Hanning window. So the curve over here in red color is the Fourier transform of the Hanning window, and then to explain why it is different from the sinc function, I have broken it into different components. So the Fourier transform of the Hanning window consists of the first part, which is a sinc function centered at omega equals to 0, which is given by this black curve over here, and you can see that this has a relatively bigger oscillations as you go away from the frequency omega equals to 0. So it has kind of larger tails. And then we have these two components where we have sinc function centered at minus pi by t, that is shown in this green color, and another sinc function centered at pi by t shown in this blue color. So what happens by adding up these sinc functions to a sinc function centered at omega equals to 0 is that these additional terms cancels off part of the tails of this sinc function. So eventually we arrive at the Fourier transform of a Hanning window, which essentially just has this main lobe and has very small tails compared with that of the Fourier transform of a rectangular window. So here is the comparison. So the black curve over here shows the Fourier transform of a rectangle window, which is essentially Fourier transform of a top hat function, and you can see these large oscillations. And when you have these large tails convolving with Dirac delta function, let's say, so imagine that you have a discrete frequency in your signal, and then you convolve this sinc function with this Dirac delta function, so you would get large spectral leakage. But on the other hand, if you look at the Fourier transform of the Hanning window, which is shown in this blue color, although it has this main lobe is slightly wider, and it's no surprise because we know that Hanning window is narrower in time domain compared with the rectangular function. So we know that the Fourier transform has to be wider for a narrow function in time domain. So no wonder we have a bigger main lobe. But because of the fact that we don't have these discontinuities at these two ends, in the Hamming window, we don't see these high frequencies. So basically, these high frequencies are required to capture this discontinuity, which is not present in the Hanning and Hamming window. So therefore, if you convolve this nicer looking Fourier transform of the windowing function with, let's say, a Dirac delta function, then you won't see much spectral leakage away from the actual frequency in the true signal, that is over here. And similarly for the Hamming window, which is shown in the red color. So slight variation in the coefficients in the Hamming window would lead to slightly narrower Fourier transform and even smaller tails. So there's nothing like a good example of this windowing process, and doing windowing is straightforward. Whenever you take a signal in an experiment, all you need to do is to multiply that signal with this windowing function. So let's imagine that we have an experiment in which we have a signal, a noisy signal, which has two distinct frequencies, let's say 10 hertz and 15 hertz. So, and there's some random noise over this signal. So I have not talked about how to perform Fourier transform of signal that has been sampled at discrete time intervals, and we'll discuss that later on. The results were computed using a fast Fourier transform, which is a way of computing Fourier transform in a very efficient manner of signals that has been sampled at discrete times. So if you have this signal which has, let's say, two frequencies, 10 and 15 hertz, in this case, this is how the signal looks like, which has been sampled at some discrete times. And now what you need to do is that you take this signal, which has already been windowed with a rectangular window, which comes by default when you take any measurement, you multiply it with this Hanning window. Which has a peak amplitude of 1, and it is defined over the time duration of the experiment. And once you do this multiplication, you end up getting a signal like this. So one might think that this signal looks significantly different than what the true signal is in the experiment, but this kind of a pulse actually helps in getting a better Fourier transform or better spectrum. Now what we do is that we compare the spectrum of the signal that we obtained from the experiment and the signal in blue color that we have obtained after multiplying the measured signal with the windowing function, which in this case is the Hanning window. And if we look at the single-sided spectrum and how to compute this spectrum, we'll discuss later. So essentially you see that if you look at the black curve, and that is the Fourier transform of the signal that we acquired during the experiment, and that one can interpret as the signal multiplied with a rectangular window. It shows this large frequency leakage over here, because our true signal of course consists of some noise, but there's these discrete frequencies at 10 and 15 hertz, but you see this very broad peak in the black signal, whereas in when we use the Hanning window, you can see the peaks are relatively narrow, and you can see that the noise is significantly less over here, away from the primary peaks, which correspond to the frequency components in the signal. So clearly you can see that a simple multiplication of the signal acquired during the experiment with a windowing function can give you much better spectrum than by directly using signal as acquired in the experiment. So another way to think about the windowing function is that if we have a rectangular window, then the signal for which we are actually taking the Fourier transform would, let's say in general, look something like this. So even though the signal is reasonably smooth within this time interval, but because of this windowing effect, or because of the fact that we've taken the signal for a finite duration, Fourier transform interprets that there's a sharp discontinuity at the ends. On the other hand, if we use a windowing function, then it will smooth out these discontinuities, and therefore we will not have these spurious frequencies or high frequencies which are needed to account for this sharp discontinuities at the ends. That is, the rectangular window results in an abrupt jump in the signal at the beginning and at the end of the time duration, and these discontinuities at the ends of the signal result in spurious frequencies that we've seen in our example, which are otherwise not present in the infinite duration signal. And when we use the windowing function, we smooth out these discontinuities. So even though we have some spectral leakage, it is certainly to a lesser extent. That is, the effect of windowing functions is to reduce these discontinuities and reduce the amount of spectral leakage by tapering close to zero near the boundaries. So you can think of the effect of windowing in two ways. One, by noting that windowing removes these discontinuities due to the effect of acquiring signal for finite duration of time. And another way is to think in frequency domain, that the Fourier transform of these windowing functions is narrower than the Fourier transform of the rectangular window, and therefore the Fourier transform of the finite duration signal, which is equal to convolution of the Fourier transform of the actual signal and the Fourier transform of the windowing function. Then what happens is that if you have a narrow Fourier transform of the windowing function, then you have reduced spectral leakage.